Hi, I'm Marissa Dubois, and today we're talking about exploring the capabilities of AI and graphics on Intel Arc GPUs. I'd like to give a special thanks for Hugh LeBay for his help on this presentation. In this talk, we'll cover all aspects of Intel's Arc GPUs by showcasing the new Xe2 architecture and the architectural improvements to it. We'll go over the new features of Xe supersampling, as well as tips on how to optimize for your Intel GPU. Finally, we'll discuss how to access and find resources for your developer needs so your platform is running efficiently on Intel Arc. Our Xe graphics journey began just a few years ago with the release of Alchemist and Raptor Lake, and since then we have made massive strides to improve power and performance for our future Lunar Lake CPUs and next generation Xe2 discrete GPU products. We've designed our new Xe2 architecture to achieve higher utilization of the different hardware blocks, improve work distribution, and reduce software overhead. Taking a closer look at each specific improvement to our Xe2 architecture, we have seen exceptional improvements across many graphics workloads. We've significantly improved execute indirect performance for compute and draw calls. Our Xi compute performance has been incredible with an uplift of 7 times higher than last generation. And execute indirect for drawing is up to 12.5 times higher on average. Our mesh shader task dispatch improvements has been a 4x rate increase, allowing for better performance in scenes with a lot of complex geometry. And our most exciting uplift is with ray tracing, as Xe2 has doubled ray triangle intersections, helping deliver amazing experiences with ray tracing in games. At our highest level of design, we have the render slice, which features 4 cores, 4 ray tracing units, and a fixed function hardware within each render slice. A render slice is the heart of allowing our Arc graphics design to be highly scalable. To build the Xe2 render slice, we started with micro and macro analysis of all graphics accelerated functions to identify improvement opportunities across various workloads. This work has led to latency reduction for various function calls, less stalls, and improved interaction between our graphics hardware and software. For our Xe core, we have seen a significant increase in performance per core, which we will describe in more detail later in this presentation. In the fixed function geometry engine, we've changed the way vertices are distributed to maximize cache hit rate, improving peak vertex throughput by 3x. And we've increased throughput by 3x for autostrip triangle lists, which are common for geometry used with mesh shading. For the fixed function pixel backend, some passes in 3D workloads like order-independent transparency or bokeh can take advantage of the increased granularity of PBE ops with 2x throughput. The pixel color cache has been increased from 12 kilobytes to 16 kilobytes per pixel backend for better memory bandwidth utilization and improved latency to memory. Xe2 can prefetch render target data in L2 caches to reduce overall latency and stalls further. A large part in the performance uplift with execute indirect is with the new native support. This native support allows for faster processing with scene traversal and culling from CPU to GPU. The hardware exposes 2 new instructions, draw and dispatch, which will handle the entire process of unrolling the Xi calls. For the fixed function samplers, some sampling reads don't require filtering or will use a custom filter in a compute shader. We've increased throughput by 2x for these operations by leveraging our L1 cache instead of the private sampler cache. Sampling operations can be very high latency, and processing these out of order helps maximize cache hit rates and reduces stalls. We've improved out-of-order support to include compressed textures, and we've added support for shader model 6.7 programmable offsets. In the high-Z fixed function unit, we've increased the high-Z cache by 50% and improved tracking for small primitives, which is common with tessellated or high-detail geometry scenes, and results in higher high-Z fails earlier in the pipeline. Finally, Xe2 has a new compression algorithm in the L2 cache that allows for larger block size and provides up to 2x better compression ratio. We've improved the fast clear feature performance and flexibility with support for sub-resources and unaligned surfaces. There have been large updates and improvements to the Xe2 ray tracing unit. In the previous generation, the Xe ray tracing unit was configured with 2 traversal pipelines for discrete GPUs and a single traversal pipeline for built-in GPUs. With XE2, all GPU implementations come with 3 traversal pipelines per ray tracing unit, which allows for up to a larger 18-box intersections per clock. The XE2 RTU also includes an increase to 2x ray triangle intersections. The Xe core has the biggest update in architecture, and it's important for developers to know that we now support SIMD16 execution. This new SIMD16 architecture has increased compatibility and efficiency. The second generation Xe core is configured with 8x 1048-bit XMX or matrix engines. Shared cache partitioning is now more flexible as we have a much larger L1 cache and SLM cache for Lunar Lake. And for specific applications, we have 64-bit atomic support. Our second gen Xe core features our incredible Xe matrix engine or XMX, responsible for handling the most demanding AI workloads. Our XMX engine allows for a variety of integer and floating point types compared to floating point 32-bit and 16-bit within the XVE. This variety of types within the XMX engine allows for faster execution at each decreased bit depth. This can speed up performance of AI inferencing tremendously. By using XMX int 8, it will have a 4x improvement over DP4A and a 16x improvement over traditional FP32. Our last generation of the Xe LPG and Xe HPG architectures featured smaller SIMD8 vector engines. Pairs of these vector engines were operating in lockstep to limit thread control overhead. Since then, we wanted to go a step further, and we have made major improvements to the new vector engine. With this new generation, we have enhanced efficiency by going to native SIMD16 support, allowing for 2 times more data elements to be executed per Xe vector engine. This architectural change also allows for a simplified control flow, allowing for more streamlined and efficient processing. Our XVE also continues with support of 64-bit floating point operations and a majority of extended math operations such as trigonometric functions and other important transcendentals for graphics and AI tasks. It's important to note that while there are many flavors of Xe1, not all included the XMX engine, but all Xe2 GPUs will feature the same XVE with a XMX engine. All Intel Arc GPUs fully support DirectX 12 Ultimate. We made the decision a few years ago to go all in on DirectX 12 Ultimate to offer developers a consistent feature set across our product portfolio. Now that we've gone over the important changes to our new Xe2 architecture, for this next section we'll share tips on how to optimize for Intel Arc GPUs. When it comes to optimizing, we have to understand a few key ideas. That is, GPU hardware is constantly changing from generation to generation, and it's important to keep up to date with the latest changes to ensure that the newest hardware can support the best performance for your games. Always query the hardware for feature support using check feature support in DirectX 12, and VK physical device features, or with VK enumerate instance extension properties for proper extension support within Vulkan. And finally, avoid using vendor IDs to disable features, and try using slower execution paths or defaulting to lower settings to avoid having problems with your game. One of the largest issues we see with many games is SIMD width, as many games feature shaders with static SIMD width, which can lead to low shader occupancy and register pressure. Asserting the correct SIMD width can help reduce register pressure and helps ensure you get the best SIMD width for better latency hiding, better instruction pipelining, reduced spills and fills from memory, and better code generation. Since SIMD is dependent on compiler choices, it is wise when developing to not make assumptions about the SIMD lane counts. Use get wave size and similar wave intrinsics to get the wave count. Swizzle operations on one hardware vendor may fail on another. Another important thing to note is race conditions can happen when SIMD is different than the thread group size. This can lead to read after write hazards and lead to corruption if one thread group depends on data from another thread group. To ensure you're getting the correct read-write behavior, use barriers to enforce this behavior. On the other side, if thread groups do not depend on each other for data, avoid barrier use as they will introduce unnecessary waiting conditions. Now let's talk about ray tracing performance, specifically focusing on acceleration structures, which are critical for efficient ray tracing pipelines. Indexed meshes are an important approach that allows the reduction of memory usage while providing faster updates. This optimization maximizes memory usage by using indices. Next, it is crucial to prepare good input for updatable geometry. When dealing with dynamic objects, we want to avoid using degenerate triangles as placeholders, as these can degrade the quality of the acceleration structure. Instead, the placeholder poses should accurately reflect the character or object, which improves the quality. Our next recommendation is to limit the use of transparent geometry whenever possible. Transparency in geometry forces the ray tracing engine to halt ray traversal to evaluate textures, which is computationally expensive. Another guideline is to avoid overlapping instances. For example, if you have a large terrain, it might be tempting to treat it as a single instance. However, this can cause excessive ray intersection tests, significantly lowering performance. Instead, it's better to divide larger instances into smaller ones. For terrains, consider breaking them down into manageable chunks. You can also leverage mesh shader techniques for skybox geometry, which are computationally cheaper. Another important guideline in ray tracing optimization is optimizing scene execution by focusing on parallelism and managing barriers effectively during the scene setup. When performing ray tracing in a scene, it is crucial to maximize the workload in parallel to keep the GPU efficiently utilized. To achieve this, we must organize operations to run concurrently, minimizing idle times between tasks. Secondly, we should aim to batch operations and barriers into groups, rather than inserting barriers individually, which can create bottlenecks. We should batch the tasks together to reduce the overhead caused by frequent synchronization. Moving on to specific operations, building or updating the BLAS and the TLAS benefits greatly from batch execution. As illustrated on the right of this slide, instead of processing each BLAS or TLAS individually, batching them helps minimize the number of barriers and idle time during ray tracing. Next, we handle the dispatch rays operation, which is the phase where we send rays through the scene. Grouping these operations helps reduce the number of synchronization points, allowing for smoother and more efficient ray dispatching. And finally, we have the compact operation. This is where we clean up and streamline the acceleration structures by removing unused space and redundant data. Like other operations, it benefits from being part of the batch execution process to minimize idle times between tasks. Now let's move on to optimizing kernel execution within the ray tracing pipeline. This section focuses on efficiently managing different types of rays and keeping shader binding tables small to maximize thread occupancy and performance. The first guideline is to use ray query when hit shading is uniform or simple. This is ideal for scenarios where the rays are fairly predictable, such as visibility rays used in shadows or ambient occlusion passes. When rays are uniform, they follow similar execution paths and can be handled more efficiently. Ray query is a lightweight option that provides better performance when the shading complexity is low, ensuring we don't overburden the kernel with unnecessary complexity for simple tasks. In contrast, the second guideline advises us to use trace ray when hit shading is non-uniform or complex. This is particularly useful when dealing with more intricate scenes such as non-opaque geometry or environments with complex foliage. Here, trace ray sorts and repacks threads based on unique shader records. Since rays in complex scenarios take different execution paths and encounter different shaders, trace ray helps manage this by reorganizing the workload for better efficiency. It ensures that rays requiring more complex shading are handled optimally while still maintaining overall performance. Another important note is to keep shader binding tables small. The size of the SBT directly affects how many threads can be effectively occupied. The rule of thumb is to aim for fewer than 200 shader records. By reducing the number of records, we ensure that more threads can be processed concurrently, improving overall performance. Another critical point here is to avoid subtables per instance. If we assign a separate subtable for each instance, the SBT size will explode, leading to significant performance degradation. Managing the SBT size is essential for maintaining a high throughput across the GPU. When it comes to GPU rendering and indirect operations such as execute indirect, there are a few pitfalls to be aware of. Issuing XI operations is cheaper than normal draw calls on the CPU, which amortizes extra work. Avoid max count 1 and no count argument buffers, otherwise you're leaving performance on the table. Use fewer XIs with high count rather than issuing XIs with low count. The more complex your command signature is, the more patching needs to happen later for each work item. Ideally, it's only actual draw arguments. Otherwise, this can lead to pipeline stalling and low GPU utilization. A better option is to group generation of arguments, then barriers, then batches of XIs using those argument buffers. Avoid barriers between single XIs, which can limit driver optimizations. Finally, if there is a chance of many empty draws or dispatches in the indirect argument buffer, consider separating prior to the compaction pass. Over the last few generations of Intel GPUs, including integrated graphics, we have worked to introduce our own velocity and luminance adaptive rasterization algorithm to leverage variable rate shading tier 2. Variable rate shading can reduce pixel shader invocations during gbuffer laydown, with the most performance benefiting forward or forward plus render architectures. With a little work, it can also be used with deferred renderers, which account for the coarse pixel offsets in the lighting resolve phase. Our Valar algorithm originally shipped in World of Warcraft Dragonflight for Intel Arc A-series discrete GPUs, and with the introduction of Meteor Lake built-in GPUs, we have introduced DirectX 12 Ultimate support, which brings VRS Tier 2 to more GPUs than ever. Due to the constraints of lower-powered integrated graphics, we have introduced a low-power mode to Valar, which uses an approximation to reduce complexity in thread dispatch and sampling rates. Valar Low Power Mode has been introduced to players of the latest expansion of World of Warcraft, The War Within. With careful consideration, it is potentially possible to gain compound benefits when combining Valar with XeSS, but some strategies may be required to reduce potential quality trade-offs. These trade-off strategies have been outlined in our paper on integrating XeSS with velocity and luminance adaptive rasterization. And additionally, we have introduced an easy-to-integrate Valar API available on our GameTech Dev GitHub site. Both the code sample for the API and the paper can be found in the resource section later in this presentation. Here, we show Valar in action in World of Warcraft Dragonflight at 4K. World of Warcraft has two modes with different sensitivities, which we call Valar Standard and Valar Aggressive. As sensitivity increases, so does performance, but with a subtle trade-off to visual quality. It's important to balance your performance needs with the quality differences, and it is possible to exclude some geometry such as alpha-tested foliage using VRS combiners. In our testing, we have seen performance speedups that can range from 5% to up to 15% in certain workloads based on content complexity and scene contrast. Next, for this section, we want to go over XE supersampling, or XeSS for short, along with the new features recently released in version 1.3 and 1.3.1. XeSS is our AI-driven upscaling technology that improves gaming performance and visuals. How this model gets plugged into the render pipeline is that it starts by jittering the camera around small random amounts, similar to TAA. Jitter offsets allow for more detailed information about scenes over several frames, which helps with creating the final, higher quality image. Next, it renders frames at a lower resolution, which reduces the workload on the GPU. Then, using motion vectors and frame history, XeSS upscales the image using our XeSS AI model to output a high-resolution anti-alias frame without the high processing cost. With our recent update to XeSS 1.3, we have brought multiple improvements while maintaining the API's backwards compatibility with previous versions of XeSS 1.0 to 1.2. We have also added new resolution scaling factors and a new AI model for greater detail reconstruction, better anti-aliasing quality, reduced ghosting, and improved temporal stability. We have also added new XMX kernels optimized for XE2 and Lunar Lake. Again, our support of XeSS has been very flexible for a wide range of GPU products, allowing for the best quality AI models on XeSS called Super Resolution, which run on our discrete products and leverage the power of XMX. For low-power platforms such as Lunar Lake and Arrow Lake H, we use the Super Resolution Light model with XMX acceleration, and for other Intel platforms and even other GPU vendors, we allow our Super Resolution Light model to be used with DP4A or HLSL kernels. With XeSS 1.3, we have allowed for significant improvements for superior control of the quality and frame rates for gamers. We have added more options for gamers to control their experience, and we have increased the resolution scaling factors from the previous versions of XeSS. Additionally, we have introduced 3 new options for gamers to select, allowing them to adjust their preferences when it comes to quality. These include the new Ultra Quality Plus mode and native anti-aliasing mode. On the other end of the spectrum, we have added the ability for gamers to choose Ultra Performance mode, delivering the smoothest gaming experience at the highest possible FPS. Since XeSS has been beloved by gamers and developers, we decided to recently introduce XeSS Inspector, which is the ultimate tool for XeSS frame analysis and insights into frame performance, enabling you to optimize and enhance every detail. To understand how to make the best insights, I will now demo XeSS Inspector. To use XeSS Inspector, you'll need to run your gaming workload and the XeSS Inspector tool. First, launch your application. Wait for it to load. Get the scene you want to look at. And then once you have your scene, switch over to your file system, run the XeSS Inspector exe file. You'll see a list of running applications. Select your graphics application. XeSS Inspector will then attach to your process and show running metrics and details of XeSS. To confirm that XeSS is running, you can disable XeSS and see that the performance metrics stop running. Then if we enable XeSS again, we'll see the performance metrics start back up. You can see the output resolution here, which is 2K, and an input resolution, which is smaller. If we change the quality mode for XeSS, we can see the output resolution stays the same, but the input resolution changes. Next, we can show some of the input buffers. In this case, we'll show the input color buffer with jittering. And then we can show the velocity buffer. In this case, it's just an overlay, but we can change the opacity so that you can overlay this with your scene. As you can see, it points arrows in the direction of motion. There's also a settings panel where we can configure settings for XeSS Inspector and the location of where to dump buffers if we want to dump frames. You can also account for how many frames you want to dump. And then we'll show you how to actually dump frames by clicking dump. Just run through your scene and then wait for the capture to finish. Then once your capture is finished, you can go to the dump location on the file system. And then there'll be a folder named after your application with the date captured. In here, you'll see multiple EXR files. These include the color input EXR files, which are color input frames. There are also the output EXR files, which are the output frames. Each of these frames has a frame number appended to it. Additionally, we have velocity frames. If we look at a color frame, we can just see it's a single jittered frame. If we run through all, we can see the jittering here. Additionally, we can see the parameters for XeSS by opening the params JSON file. And in here, you'll see all of the XeSS settings, including jitter offsets and jitter scale and velocity scale. And then finally, we can open the velocity buffers and inspect the velocity in the scene. Hopefully, you learned how to use XeSS to best fit your needs as a developer. To further make an even better experience with your games, we want to show you where to find developer resources that can help you optimize your game. To find more articles and information on game development for Intel, hardware and software, please visit github.com/gametechdev. And to learn about XeSS, please visit our GitHub on XeSS from the link on the screen. And for Valar and XeSS integration, please find our white paper on the third link. Many amazing tools from Intel are available to help developers deliver the highest performance of their games on Intel platforms. You can find more information by going to gamedev.intel.com, where you will find tools such as vTune, GPA, XeSS Inspector, and more. We also have Gits, which is a toolset for capture and replay in Vulkan, OpenCL, and Intel's One API. Another tool is PresentMon, which is also developed by Intel and is used for capturing performance data in graphics APIs such that developers can analyze and gather performance metrics such as frame rates, frame times, and GPU durations. We hope that we helped you on your journey learning more about Intel's Arc GPU architecture. Thank you for joining our talk.